Welcome back to The Explainer. Today, we're diving into a genuinely fascinating evolution happening right now in artificial intelligence. We are moving away from those basic, forgetful chatbots and looking at advanced systems equipped with actual long-term memory. We're going to break down exactly how engineers are literally mapping human cognitive psychology onto silicon to create an AI that doesn't just process text, but actually remembers who you are. So let's start with a really fundamental knowledge gap. Think about the AI tools you're probably using today. Modern language models have massive context windows, right? Some can ingest 1 million tokens at once. So why are they still fundamentally stateless across sessions? Why do you have to start from absolute zero every single time you open a new tab? Well, the answer lies in a simple but absolutely crucial truth. A context window does not equal memory. Expanding a context window is honestly just like cramming for a test. The model treats all those tokens roughly equally in a flat, temporary workspace. It has zero concept of what is truly important versus what's just incidental noise. It's a temporary buffer, guys, not a lasting architecture. Here is a quick look at our roadmap for today. We're covering the stateless agent problem, mapping the memory taxonomy, the active memory lifecycle, the context saturation gap, and finally, real-world AI applications. Let's jump right in. Okay, part 1, the stateless agent problem and how we escape that flat context. Consider the sheer contrast here between a completely amnesic system and one that actively builds a digital identity. On the left, we have the stateless LLM. It suffers from what we call the stateless agent problem. It completely forgets you the exact second the session ends. And just pumping it full of tokens, that leads to high latency, massive API costs, and the very real risk of the model hallucinating or missing key facts buried in the middle of a massive prompt. But look on the right. Agentic AI relies on hierarchical memory. It actively filters, encodes, and maintains persistent knowledge across sessions. It's actually learning over time. Which brings us to part 2, mapping the memory taxonomy. Let's look at the actual anatomy of agentic memory. We have to start with the physical substrate. Basically, where the memory actually lives. Internal substrates involve baking information directly into the model's parametric weights. But that can be rigid, and it's super prone to something called catastrophic forgetting. External substrates, on the other hand, use databases like vector indexes. This is a real game changer because it allows the agent to read and write an arbitrary volume of historical data on the fly, completely avoiding the massive computational overhead of retraining the whole model. Now, moving up the cognitive staircase, we enter the functional mechanisms. First step is sensory memory. In us humans, this is just a millisecond-level buffer. In AI, this maps directly to token ingestion. Sensory memory acts as this rapid perceptual filter. It strips away redundant noise, so the agent doesn't just drown in irrelevant context before it even starts reasoning. Once that information is filtered, it lands in working memory. This is your active, flat context window, where the agent actually does its immediate reasoning. It's holding the goals, the intermediate states, the tool results it needs right this second. But remember, working memory is strictly temporary. The tab closes, and it's gone. So how does the AI survive beyond a single session? That's where episodic memory kicks in. This layer keeps a time-stamped autobiographical log of what happened during a specific task. Think of a really complex coding debugging session or a lengthy back-and-forth customer support ticket. The agent remembers the sequence of events and decisions. But this memory is usually scoped by a session ID, and it's designed to eventually expire or get compressed when the task is totally finished. Deeper still, we hit semantic memory. This is the holy grail of personalization, the persistent knowledge base. It extracts and abstracts durable facts, your user preferences, general knowledge, stuff that definitely does not expire when you close your laptop. It's how the system remembers for sure that you prefer Python over JavaScript or what city you live in. There's no single conversational episode attached to it anymore. It has just become a stable, learned fact. Finally, we have procedural memory. You can think of this as the behavioral center. It encodes the reusable skills, the instructions, and the tool use policies that the agent has mastered over time. It's the how-to knowledge. This implicitly improves the agent's actions and workflows, allowing it to become way more efficient at actually solving real-world tasks. So stepping back for a second, a really crucial point here is identifying who the memory actually serves. Is it user-centric or agent-centric? User-centric memory is all about you, building a customized profile of your preferences to tailor future interactions.
Agent-centric memory, however, is all about accumulating operational knowledge and task experiences to make the agent itself smarter and more capable of handling long-horizon environments.
All right, part 3, the active memory lifecycle. Let's look at the metabolism of the agent. So, the anatomy we just looked at is static, but memory in practice is highly dynamic. These 5 steps form a continuous read-write loop running constantly in the background. Agents index raw streams, retrieve relevant context, and consolidate records to correct conflicting facts. And here's what's truly fascinating. Explicitly compressing long interactions into semantic facts and deliberately forgetting outdated info is just as critical as storing it in the first place. Without strict updating and forgetting, retrieval just evolves into a complete mess of contradictions. Moving on to part 4, the context saturation gap, where we stress test this whole architecture. You might be wondering, how do we know external memory provides real structural value? Well, as models process millions of tokens, they risk context saturation, where answers technically just fit in one giant prompt, but the model struggles to find them. The context saturation gap measures the performance delta between a smart memory-augmented agent and a brute force full context baseline using the exact same model. A large positive gap proves the memory system is actually reasoning, organizing, and filtering rather than just blindly scanning a bloated prompt. And speed matters immensely here. 32. During testing, researchers found that strict, recursive, hierarchical paging systems can actually exceed 32 seconds of user-perceived latency. Obviously, that is completely impractical for an interactive chat. It just proves that lightweight, precise retrieval indexing is vastly superior to forcing a massive context read for every single generation. Finally, part 5, real-world AI applications. Let's see this memory in practice. In the real world, memory systems are shifting AI from simple, utilitarian tools to persistent companions. Look at education. Agents are beginning to act as cognitive digital twins of students. They can track a learner's progress over months, map complex educational concepts, and even explicitly simulate knowledge decay using the Ebbinghaus forgetting curve, so they know exactly when a student needs to review a topic. And if we pivot to healthcare, memory allows agents to track longitudinal health trends. They rely on affective continuity to monitor a patient's emotional trajectories over time. This means they can actively adjust and personalize therapeutic strategies across multiple sessions. It's incredibly powerful. As we wrap up this explainer, I want to leave you with a bit of a provocative thought. We've just seen how these multi-layered systems pull in your facts, your preferences, and your emotions to build a lifelong cognitive digital twin of you. But as these agents learn exactly how your mind works, who ultimately owns and controls that digital reflection? The privacy implications here are absolutely profound. Thank you so much for joining me today to decode the architecture of AI agent memory. See you next time.